Okay, so it's time to begin. So yeah, let's begin our last part of panel discussion. So yeah, so let's begin. So if you have any questions, then please raise your hand, or you can come to the microphone. Not ready yet? Okay. Then let me begin with my question. Hold on. So yeah, as being a professor myself, I often see student having a good GPA doesn't necessarily be a good researcher. So yeah, there is a correlation, but may not be that strong. So I'm curious what the speakers today is going to have idea about that difference, and I wish them to give some comment or recommendation to you guys how to study to be a good engineer. So who's going to start? Jali?
Sure.
Thank you very much. So that is a good question. But before I answer the question, I really want to encourage people in this hall to please ask your questions. This panel is meant to answer questions coming from you, not from the moderator here. So, but I think it's a good idea. These are great questions. So I think I have some good news for you. And the good news is that, yes, it's true. It's not just the good marks or the good grades do not necessarily correlate with excellent research ability and research potential. So it happens that sometimes the students who have their own mind and they may not follow exactly the instructions as come from professors, they may not get the good grades, but in fact, those are the ones who are thinking for themselves and they may not just follow somebody else. You can always get good grades if you just follow the instructions, and that's easy. You know, they tell you exactly what the textbook is. Even you have access to the previous exams, perhaps. You can go ahead and do really well on the exams. But this always shows. So when you see somebody has very good grades, all close to 100%, you start asking yourself, is this person just following the instructions? Do they have their own ideas? And then that is something that comes out during interview. And I must admit that some of my great students that I've been teaching or doing research at University of Toronto for the past 25 years, but I can tell you that I've had many students, PhDs and masters, but some of my most successful students that I really respect a lot at the time and now are the ones who didn't have a very good GPAs. So this doesn't mean that, of course, you go ahead and ruin your GPA just to become a better researcher. But the idea is that, yes, you can show yourself, and of course, in the interviews, it will become very clear that it's not about grades, it's how you think and about your innovation and your research ability. So.
Maybe I can continue. First of all, I think this is a great question. I also completely echo what Ali just mentioned. I think in real world, in practice, there probably a less correlation than what we have believed in terms of the correlation between the GPA and the creativity as a researcher. I think it's very important, and based on my experience of supervising many PhD students and the postdocs and in my research group back in the Georgia Tech and now at ETH Zurich, Switzerland, I think that great researchers are coming from the type of people who have the courage to think out of the box, right? And we can also kind of define, well, it's hard to say, and what kind of research results are great research results. And we can also look at different papers, and there are very different type of papers. Certain papers are improving the state of the art bit by bit over the years. Those are very important papers, benchmarking papers, don't take me wrong, because the industry and the academic world, we need to see where the limits are. But there are also type of papers, often coming from academic group, by great researchers, you will see complete new ideas out of blue, right? Which solve the problem, and largely advance the state of the art. And I think those are the papers coming from people who have the courage of thinking out of the box.
Okay, I believe the good GPA student produce the good research because I am hiring only high GPA student. Yeah, because the creativity and innovation is the key, most important in your research in the circuit design, right? I believe the creativity and innovative research comes from the good attitude and the strong academic background. So high GPA, I believe, verify you have the academic background and your good attitude toward your research and study, right? But still, some of students who have a low GPA show the great performance, yeah. But most of the case, he has or she has a good attitude toward the research on study. But I would like to recommend getting a good GPA. This is my conclusion.
Yeah, from the industry perspective, so I am curious what you are thinking.
Okay, yeah, I found this very interesting, so I tried to think it for a very long time. So I think to get good GPA and do good research requires different techniques. Now, to get good GPA, the techniques you need is to try to find the solution and learn it and copy that solution. I would say that. If you have a question, you're starting from finding the solution. Where is the solution? And try to get one of them. But the research is totally different. Try to good research is try to understand the problem, not to try to find the solution first. So it's right, two different techniques. GPA, have a question, find the solution first. Research, have a question, try to understand what is the question. And that will come out new ideas. Because when you're starting from understand the question, then you are not limited by the other solutions. And sometimes the question is so clear. Once you will define the question, the solution it automatically come out. I always will use this example to say someone else. If you make someone unhappy, you can buy a lot of gift to him. But if you know why he is unhappy, probably can say one sentence, then it's done. Okay? So we'll define the question, we'll give you new method to solve the problems. Yeah, I think that's the difference.
All right, it's a very interesting question, and I agree that the good GPA student may not be 100% perfect engineer, but in my experience, there is a very strong correlation. Very, very strong correlation. Actually, almost a 4.5 GPA student may not be the top engineer. However, they are very, very, very good engineers. So, actually, in industry, you are not working alone. You are working as a team, and a team may not be consist of all the genius. Just good enough engineers are enough. But if we want to find genius, it requires a lot of cost in industry. But GPA is very, very good tool to find good engineer. And actually, good GPA students, they are very sincere. They are very good attitude of learning, and in many cases, they follow the team rule, and they are very supportive in many cases. And I think in team or a few juniors are enough. Not always everyone needs to be. Again, the very high GPA may not be always, but I still think it's a very strong correlation.
Thank
Yeah, thank you for good question. And, actually, I'm not a researcher, and I don't think I'm a good engineer. But around me, some engineer or some researcher, I think he's very good researcher, great researcher. I think there are some common features that they think deeply. So I think that this is a little bit different from the way of getting a good GPA. I think I agree that GPA we can get by following the instruction and getting an examination we can get. But good, I think great researcher, great engineer always think deeply. Mean that they don't believe the common knowledge. Like, for example, there are some of the circuit is prepared and they develop some of the software. They always think why this is needed. What happens if this module is removed? Such kind of, they always think what is a basic concept and what is, they are always thinking the simplest element, the essence of their research field. So I believe that great researcher or great engineer has always need to think such kind of think deeply and always have a question that the common knowledge, I believe.
Thank you. So I have following questions then to Ali, Hua, and Yunxiang. So if you are, you know that we have some correlation, GPA and good engineer, right? So if you are not seeing, I mean, actually you're gonna see student GPA, right? Other than that, what are the important points when you review the applicant's document?
So I must admit that I put a lot of emphasis on an actual interview with the candidates. So I will not just go look at their GPA and I will conclude that they're good. Obviously they have reference letters, some of the professors who write about them, and then if there is any deficiency in the grades, usually it's addressed by the supervisor or a person who's writing a reference letter. And sometimes students themselves, they write in their own statement of research why some grades are very low. And you can always read those and read between the lines, but then when it comes to the interview, you find out, yes, this person, for example, may have not got a great GPA because he decided, family issues, and he decided to take a leave of absence, and that caused the grades to go low, but then you see all of a sudden in the final years the grades improved, and then you ask them one or two questions, and I think it was good. I'm happy at least to see some of us are on that side, that you ask a question and see how the person deals with that question. It's not about the answers, it's about the process by which you take a question, analyze it on the spot, and think about it, and then hopefully come up with an answer. I think that those are some of the criteria that I use as we evaluate the candidates.
Yeah, as a matter of fact, I'm doing something very similar too, and I rely also a lot on the actual interview process. Right? I often will ask students and for questions that may not have actually the fixed answer, and very kind of open topic questions, just to really to see how the student would like to think and on the feet. So and also, I look at the reference letters, of course, and I will also look at the past experience of the students. Right? I think that's very important as well. Yeah.
Thank you. Yeah.
Yeah, I think from the papers, I think it's very difficult to tell. So it's all basically based on interviews. So interviews for industry company, I think we need all different kinds of people. So first one is if the person is very easy to talk with and probably a very good team worker, and he will be able to work on a lot of jobs, just as like Jung just mentioned. Sometimes good enough is good enough. And sometimes we will ask question about, we will ask him to present his work, and we ask some question like why you choose this, why you choose that, and that will become to the issue that I just mentioned. If someone answers, oh, I don't know, I just reference some paper where I found that, oh, that one used a lot in different works. I think that is useful. And someone will answer why he's choosing that one. Then you will tell if this candidate really think about this question before. I think right now there are a lot of people just answer, oh, that is because of what. But you will realize that is copy from textbook. And if there's something different, then probably that candidate think that kind of things deep before. Yeah.
Thank you. Yeah, I hope those answers can be good tips for you guys. Okay, yeah.
I have a question about how to plan the research in the PhD, because it will take a long time for firstly research the background and the design and the simulation the circuits and plan the layout and waiting for the tape out. After the tape out, you need to design the evaluate board and waiting the package, and then you also need to testing, but it will maybe take about 1 more years. So the time for study is not too long. So how to plan the research for the PhD and to make the PhD more experience?
Okay. Work and research balance. So, could you? Who's gonna answer first?
Maybe I can get started. And so, yeah, I think in my in my group, right? So a new PhD student coming to the group, and typically, you know, the planning is very important. Why? Because typical PhD 4 or 5 years. But actually, the time is not very long, right? Considering the long lead time of our research projects, right? Typically, few months of the design and sometimes even longer, and the months of tape out, months of waiting for the chip to come back 4 or 5 months, and then the testing, and easily 1 year or over 1 year it will be needed for one project. So to really design this more efficiently, I normally encourage students at the beginning to probably junior students to shadow and work together with a senior student and as a partners and for the first year. And this helps the junior student, besides taking the courses, also getting the ready for the research environment. And I typically design those as a warm-up project for the student. Right? So for sure it will work, and the purpose is to get familiar with the tools and the measurement or the setup. And then I would recommend the students to probably focus more independently though on building block kind of circuits, right? So something like a smaller scale, but easy to handle, and then really get down to the details, get down to the bottom. And the later part of the PhD, probably the student can work on more system level and the projects, and come back hopefully to help supervise and mentor junior PhD students. This is how actually I would envision basically the way I run my group. Yeah.
Sure, yeah, so I think the approach is very similar in almost all the research groups. If you're going to a group that you're the only student and the first student, the story will be different because you need to build up the whole process. But typically, if you go to a relatively established group, that means that you're going to deal with some students who are in the second year, some in the third year, some in the fourth year. And these students really help each other, and that's very important as part of the style of doing research, is that you're not going to be alone. You're going to be with a group of people. And again, as Hua mentioned, you often have students that while you're entering the program, they are in the last stage of their program. They're already testing their design. So if you get involved in testing, that will give you a good idea for your new design, that when you're going to design, you have to make sure it's testable. Because you find out that that senior student made a mistake, and now he could not find out what the bug is. He just knows that the chip doesn't work. But then you ask him, why don't you look at that particular output node? He says, well, I have no access to that node. Then you learn through that process that, watching your older brother making mistakes, that you will learn and hopefully you don't make that mistake. It's not always learning through negative, sometimes you also get surprised at how thoughtful they were and when they were designing this. So now they can debug it easily. As you know, you mentioned, you go ahead, design, you fabricate, you test. You didn't mention the debugging stage. That could be another 6 months all of a sudden on top of what you did. If you made a mistake, or it just happens. Not everybody is immune to this. You find a bug, whether you're Einstein or whoever. You design a chip, there will be bugs, and you cannot make it work on the first day. It takes a while to essentially bring things up and make it work. So you have to be patient, persistent, and I guess during that process, you learn through everybody else how to handle that situation.
Maybe I can also add a little bit more. Another reason why most of the groups, and we also structure the PhD in this way, and there's another reason, okay? So PhD students coming out of our research groups, right? And the research papers and research results are very important. But don't forget, those are only part of the outcomes. And the other part of the outcome is actually the professional training of the students. That's equally important, sometimes very, even perhaps even more important. And at the beginning of the phase, work together with senior students, this to show that, okay, the new student can work as a team member, right? Is advisable, is important. And then later on, the student can design and work on a project independently. This shows that the person can fly solo. That's important too, right? You have to be able to stand by yourself. And then later on, the student can lead team project, come back and mentoring junior students. It shows that the person can work as a team and also as a team lead. I think this is, besides the technical papers and per se, this is another important aspect of the training for the PhD programs. I think the students with these characters will also really benefit from that in their future career.
Probably just a couple words. So I think during my PhD, something I learned is must think before you do. That will save you a lot of time. My experience is you have to work really hard, and after 1 week, I found all I've done is nothing, just wrong. So, and I think again, I should know that 1 week before. I should be able to predict that method is not right before I do it. Okay. So I think before you do will save a lot of time. So you will be able to do a lot of things in limited time. Then, so the plan first, then do. Don't just do. Then it will just recycle many times. Thank you.
I have one comment for your question. This is a good question. I'd like to say, please don't be afraid for your consuming in your PhD program, because our fundamental goal pursuing the doctoral program is not outcome of paper. So actually the procedure of pursuing the doctoral degree, that is very training course for be the professional, right? So even though the most of the tough point is that we have to implement the real silicon device and we have to verify, and all the procedure is very painful, right? So even if I have a good idea, we have a big risk to fail the working the chip, and we fail to find the troubleshooting solution, right? But all the procedure is very valuable for becoming a professional engineer.
Okay. If we don't have any more questions, answers, then Would you come forward?
Hello. I wanted to ask what you are thinking about, like the open source projects and the future about it. For example, the Skywater, and what are the impacts on the industry and on academia and projects.
So who's gonna answer about open source hardware?
Yeah, thank you for your question. I think that the open source and EDA tools and the Skywater project is very, I believe that this is a very important for the future of the semiconductor research. And I think that this is important to, how to say, increase the number of researchers that implement semiconductor, because we can freely use the open source tools, and we can tape out the very lower cost. So I think that students and other kind of students who are interested in making semiconductor, I recommend to freely try to Skywater and other kind of low-cost tape-out project. I believe it have an effect of increasing the number of researcher or semiconductor engineer, and it finally becomes a good effect to semiconductor industry.
Okay. Until a few months ago, I thought that open source is much better than closed one. But these days I'm quite confusing, because the number one company is closed type, such as Apple and NVIDIA. They are not using open source. They made the ecosystem by their own one. So it's a very interesting thing. So for example, for UCI, it's a very standard trend to make a standard interface to make the interoperability among the different companies, but NVIDIA is making their own die-to-die interface, NVHBI, and their technology is the number one. And also the other side, Apple, everybody may know, it's very interesting trend that, and also for the UCI forum, there are only two companies that are not joining, Apple and NVIDIA. So it's a very interesting trend. So still I'm thinking about that. I didn't find the answer yet.
What I think these open source are enabling, as they use the phrase democratizing IC design, is that it all of a sudden makes it available to a lot of people, especially in countries where otherwise they have no access to silicon. So yes, you do not get access to 7 nanometer technology. You will get access to much older technology, but for learning purposes, especially at the undergraduate level, you really don't need to jump into 7 nanometer technology. In fact, I would advise you against it, because you will just leave the area probably if you're faced with the issues that 7 nanometer technology may bring you as a starting point. So those are not really good starting point. The good starting point are the good old technology where you have 90 nanometer would be more than sufficient. Transistors behave really nicely. You don't have as much variations, and then you can test. So I think these open source tools and open source design kits are really good for education, perhaps at the undergraduate level, when you don't need to use your supervisor's funding or university funding. It's all free, all open source. But once you reach to the level of, let's say, masters or PhDs, then you realize that you probably cannot publish anything with the ones that you're going to use freely. Now you have to rely on more advanced technologies. And yes, all the advanced technologies are behind a closed door. You have to sign an NDA. You have to put your life online so that you get access to them. And those are very difficult, but those are the ones that if you're at a PhD level and you're trying to innovate, most of the time you need access to more advanced technologies that are openly available.
Well, then I have a following question for Ali. So if we think the AI or software, then open source makes the technology development very fast, right? So according to Ali's comment, it sounds like open source for hardware will remain as just the educational purpose. So you don't think for hardware implementation, open source is not going to work.
Yeah, so this is a topic of great interest of whether AI and ChatGPT will be able to replace you or replace all the circuit designers. And my belief is that if you look at where the success of AI and ChatGPT or alike are the ones that you have a lot of data for training. And the fact is that for circuit design, we don't have enough data to train anything of significance. Yes, you have the textbooks and you have maybe some open source that are old in a sense in terms of design kit, but those are not at all sufficient to train a circuit designer at the AI level. So I think that most of these companies, if they have any designs of any value, they do not release it publicly. So that could not be used for training. Somebody was asking me, in fact, during the break, well, what happens if major company, of course, they have a lot of designs. But if you look at even one major company, how many designs do they have? It sometimes takes the whole entire year, maybe more than 200 engineers, to come up with one microprocessor design. And if you look at the lifetime of a company, they may have 1,000 designs. 1,000 is not enough to train a large language model or anything like this. So I think we are far away from anything in terms of AI taking over circuit design. So you're all safe, your jobs are safe. Enjoy circuit design while you can.
Thank you. Yeah. Okay. Yeah. Oh, okay.
Hello, I'm Min Jae-pa from the GIST in the Korea. I think all of you are very good researchers, and I just wondering that what motivates you to do circuit design. Thank you.
Yeah, I think we can start from there and then.
Yeah, actually, I am still a PhD student. I'm not a researcher, but I'm very interested in designing the SOC or digital design. And this is a great question, but a difficult question. The first my answer is because it is interesting. But yeah, and we can. So in my case is that I am a digital design engineer. So and basically my work and my microarchitecture research field is using the Verilog HDL or such kind of microarchitecture simulator. So the first motivation of my interest in this research field is that we can, for example, we have a FPGA. We can realize just digital design into real circuit. This is a very interested in for me. So such kind of I remember that this is a bachelor degree when I was a student. So I started to interested in such kind of digital design. So I believe such kind of first trial of getting to getting some of making some circuit is a good first step of make interested in to research the semiconductor.
Okay, first, strong motivation is making money. Yeah, just kidding. It's not enough, and we can make the world better.
Yeah, okay. The reason why? So I think in general, in electrical engineering, there are different areas, and different area require different kind of talents. Okay. So let me talk about why I choose analog circuit design. I choose circuit design, analog circuit design, because that is do not have so many mathematics. Okay. There are only resistors, capacitors, and inductors, and everything can be modeled as these three components. So all I need to learn is these three components. Okay, so I found that is very suitable for me because I don't want to get involved with a lot of equations. So I think it is very important to find something that is suitable for you. And one suggestion is you can use a ChatGPT to check. So once I asked the ChatGPT what makes us a good analog designer, and the answer is quite accurate. So if you want to know which domains suit for you, you probably can ask ChatGPT.
I'm not yet a good engineer, and I'm not yet good circuit designer, but I try to becoming more a good circuit designer. I'm still working on, but why I select the circuit design field is actually very similar, because the circuit can be analyzed using very simple concept, the V equal IR, the Ohm's law, the KCL, KVL. This is a very simple concept, but why circuit always difficult, right? So this is very interesting for me. So I am finding way to what is the good circuit, what is the more intuitive, and what is the more straightforward circuit design. Okay, so aside from this, I would like to say that the circuit design research topic is very good for your surviving and very long life topics, because this is very easy, because easy to follow the very fastly changing the tech trend, right? So for example, for my case, my major field is the power converter, the power management circuit, discrete driver circuit. For example, the power. So I just changed the keyword: power for smartphone, power for mobile, power for the server system, power for the AI processor. So it is very easy to follow. I would like to say the circuit design is very fundamental and very versatile, and always the electronic system need the hardware, right? So it is very easy to follow the fastly changing the tech trend. So display, just the display driver for LCD, display driver for OLED, and display driver for micro LED. Just I changed the topic, but my fundamental is the same, right? So I think all you guys, if you already select the circuit design, is your right the topic, congratulations, your choice is very nice. And if not yet decide, please select the circuit design. Digital circuit okay, and analog circuit is also okay. But this is very rewarding topic. Thank you.
So I am more like analog and RF and circuit designer by training. So, well, the reason I like it, this area, of course, I echo many of the points and other panelists have already mentioned. And just looking at the circuit design as a technical field itself, well, the reason I like it because it really requires a level of creativity and a level of insights. Perhaps that's the reason why we have the session today, circuit insights. And the insights are coming from different level of understanding, a different level of abstraction. And if we look at circuits from different levels, and often you'll have new ideas, and this is where the exciting thing about. But at the same time, don't forget, our goal is to have a physical working system, electronic system in the end, physical chips. So it is being bounded by, mathematical rigor and physics constraints and a lot of practical design limitations. So it's a real thing. And I think the combination of the need of creativity and it's also well connected with the physical world, I think that's the reason why I really like it.
Yeah, so I think we are really blessed with a lot of great, enjoyable concepts in the area of circuit design. I don't know, I'm sure that if you go to any field and you find people who are passionate about it, you'll find out there's a lot of beauty in all of those areas. But I must admit that I was exposed to this area and I fell in love with it because I feel that the area of circuit design is full of those great concepts that when you look at it from the outside, it looks very pretty, And then when you go inside, you see there's really a major beauty inside that you cannot even see it from outside. So once you enter into the field, you'll discover those. I disagree that this is easy, there's no math. There's a lot of math behind it. But then you need to go inside, and then you'll find out that, wow, this is all the math you wanted, this is all the physics you wanted, and this is all the poetry you wanted, for that matter. At the high level, I appreciate it, and I must admit, I didn't appreciate this when I first started going into the electronics, because you just see what other people are telling you about it. But then later on, maybe during graduate studies, and I discovered that really what we're doing as circuit designers is that we are controlling electrons. That revelation that this is what you're doing. You have a problem in hand, you want to do something in the world, and you would say, okay, how do I implement this differential equation that I want to solve? And then you say, well, I'm going to employ electrons to help me doing this. And say, how could you use electrons to do differential equations for you? Well, because a capacitor is taking derivative, right? Or it takes integral, depending on how you apply current and the voltage, or vice versa. Resistor is providing you the first order, proportional. You have integration, you have derivative, and now you can combine them, and you can solve any differential equations. That is math inside physics, right? And that is a combination that you can't find it anywhere else. And so once you get to that realization, I mean, it is so obvious today. You all have cell phones, and you don't think about it, that this is a miracle in your pocket. Can you imagine you're sitting here and you're talking to your family 2,000 miles away, and you don't even question it? That how is that possible? I mean, think about that. We talked about waveform engineering today. How do you take this, your voice, and it travels and it goes somewhere else? I don't know. This is absolutely mesmerizing to me, even though I've been working in this field for, I don't know, the last 40 years. I don't find it. It's just this amazing field.
Yeah, thank you for the answers. Well, speaking of beauty of analog and job security by being circuit designers, not only to Professor Kim, but nowadays if you go to like a CAD conference, then lots of people are doing analog design automation by utilizing AI. So simple circuit designs like with OPM having a well-defined architectures, then AI can generate good design. So different from like 10 years ago, I'm very afraid that whether students just like having a bachelor's degree, can they work as a circuit designer? Or should they get all the PhD degree? So I have a question about that. So AI can design circuits, then what should we do as an engineer, circuit designer?
Okay, this is my first answer is for this. This is the reason why you have to pursuing the PhD degree, because very conventional circuit can be very easily optimized by the AI, right? So in more and more, we need to more innovative design or topology rather than optimizing the parameter values, because the AI win your ability to optimize the values. And I'm not expertise in the AI-based CAD or design automation, but for my case, getting one result from the simulation, so we consume very long time for the 1 week for measuring just 1 millisecond. So that is very consuming. So the AI, this is actually based on the deep learning. So many data set is necessary, right? So getting the many data set is very computational power, high computational power is necessary. But I believe a very genius human can still beat the computing power by using the intuitive understanding and intuitive design. So this is my conclusion.
Any answer to add?
I think this is, I think it's both sides. So sometimes we will find the designer, how they do the design, they just change the size until the specs are passed. So that is something AI can do. Okay. Just that we do not have that completed environment so far. We probably already have some environment for specific circuits. Just like the professor you just said, if you have a simple architecture, basically AI can do everything. Okay? But for the more complicated one, and we haven't have that kind of environment because it's too complicated. So, but sometimes the designer is still doing that kind of tuning to tune the circuit. And I think that eventually that part AI can do, as long as people still keep working on the tool environment, then they will be able to do that. So that part, I think that is something we should try to avoid. You just do a design by tuning the size. But of course, a designer need to do is to change the architecture. They change it, like add one device or remove one device. That one, I think AI is difficult to replace because it changes architecture. So what we need to learn, I think, is to understand the basic functions and tell AI what we need to simulate. Of course, you can add a device and then try to ask AI to optimize that device. AI becomes a tool to support your design. But AI probably not able to help you to design or create a new architecture. I think that is my answer.
Okay. These days I am working closely with EDA companies, and I am pushing them to accelerate their analog migration or analog design automation. And they are announcing that they almost get there with AI-based design, and they announced and published in CAD conference. And in reality, some of them are exaggerating, some of them are lying. So it's a good news. Still long way to go. So yeah, this is one of the reasons is the lack of the data set. And another reason is actually most of the mature process-based design would be achieved within a few years, but every year the most advanced processes are developing, and it's very difficult to match the model-hardware correlation. So every day, model-hardware correlation is changing for advanced node. So it's very difficult to estimate. And also, the technology setup for some automation is very time consuming. So for example, even for visual band gap reference migration, it takes a few months for migration for advanced node, but because of the technology setup, process setup, but even just junior engineer can convert within a day sometimes. So still it's a long way to go, but sometimes it will be achieved for mature process, but still it's not that easy for advanced process. So still circuit engineer may not lose their job.
Yeah, it seems like we still have hope, right? Okay. Okay, yeah, all the discussions were very interesting. It's about the time to finish. So yeah, hope you guys had a good time here, and it was hope it was valuable to you. So please thank the speakers and yeah, give big hand to them. And yeah, I also appreciate you guys for attending this event. Thank you.